Hi everyone and welcome to EE 326 Lecture 20. Today I'm going to be talking about a new topic, the topic of feedback. You can refer to your book in section 11.1 for feedback. Okay, let's get started. So up to this point, we've really been thinking about what we would call the open loop characteristics of circuits. And that is, if we took an amplifier like this amplifier shown here, and we connected some inputs to it and we looked at the output and we said, the output is A times V plus minus V minus. It's what we expect from an op amp, right? But it turns out that the gain of those op amps, they're made with transistors on the inside. And these transistors and the other components inside vary. And they vary considerably. And so, for example, if you looked at a 741 op amp, which is a very popular one, and you look at the data sheet for the 741, you'll see that the typical gain is about 2 times 10 to the 5th, and the minimum gain is much lower. It's 5 times 10 to the 4th, according to the data sheet. So you can see this really large variation in what you can expect from the gain. So for that reason, when we're building electronics, we rarely use op amps in what we'd consider an open loop configuration, like this. Instead, what we like to do is we wrap feedback around it. In the circuit on the bottom, you can see we have transistors R2 and R1. They constitute a feedback path where we can take some signal from the output and feed it back to the negative terminal. In this case, it would be negative feedback because it's going to the negative terminal. But still, what these can do, this is what we'd call a closed loop configuration. Closed is in the sense that we have feedback that's closed around the amplifier. And this is how most gain and most amplification is done on chip and in electronics. And we can see why we might call this negative feedback. Like suppose, for example, I had a small delta V going up on my input here, on the positive input. What we'd get at the output is a large delta V, right? Because we have some gain. And now we're going to feed back that signal, and some portion of it is going to go to the negative terminal. So we're going to get a small delta V on the negative terminal. But now the difference, V plus minus V minus, has actually gotten smaller. And so our output, the change in our output is actually going to go down. And so the negative feedback actually controls what's going on at the output. Okay, so let's talk more about this. And you've seen feedback before. This is an example here, right? This is the inverting amplifier. Our input is VI going into R1 into the negative terminal. Our output is VO. And if we have a finite gain A, we can see that if we work through this as we've done in 323 and other classes, we get a result at the end that says V out over VI is approximately equal to minus R2 over R1. And so we can see here that if the gain A is large, then we get this result where V out over VI is approximately minus R2 over R1. That's the inverting amplifier configuration. All we really need to do with our amplifier is make an amplifier that has a really large gain. And this is true. So if it varies by 20% or 50%, as long as all those values are large, then we're still going to get a controlled gain here, this minus R2 over R1, that depends on the ratio of resistors. And it turns out that we can control resistor ratios very well. Even on chip where we have big variation in components, if we lay out two resistors next to each other and they have different resistor values, they'll both vary and the ratio will stay very, very close. So that's a big advantage of being able to use ratios for this. So there's some other benefits of negative feedback. The one I just talked about is it desensitizes the closed loop gain to op-amp variation. As long as the op-amp gain is big, then our closed loop gain is desensitized. There are some other advantages. For example, it can expand the bandwidth of a circuit, and we'll show you how that happens. We'll talk about this in this class. You can reduce noise, you can reduce distortion, and you can control or change the input and output resistances through the use of bandwidth. Now, we're not going to talk too much about these three here, but we are going to talk about these first two in this class. All right, so let's talk a little bit more about feedback. So this concept of negative feedback was discovered in 1921 by an electrical engineer who was working at Bell Labs named Harold Black. This picture here shown on the left. And the story goes that he was taking the ferry to New York from New Jersey across the Hudson, and he was bored, and the only thing he had was an old New York Times. And he jotted down this concept of negative feedback on the New York Times. This is the image of it on the left here. And it's become a hugely, he was working on telephone amplifiers, it's become a hugely important discovery in the world of electronics. In fact, if you read Wikipedia, it says one of the most important discoveries of the 20th century. So let's try to figure out what this is exactly and how we can identify it, how we characterize it, what are the terms we use. So one thing we typically do is we make simplified block diagrams to try to understand the behavior of circuits, and this is no different. So in this case, we've made a simplified block diagram of a negative feedback circuit. So you can see we have our input VI and our output VO, just our input and output voltages. And we have some gain here, A. This would typically come from a transistor amplifier. That gain A, by the way, is called the open loop gain. So then we feed our output signal back through this term called beta, and that's called the feedback factor. And it feeds back and then subtracts from our input, from VI, the difference between our input and the signal that's fed back, then goes back into the amplifier and is amplified by A, and this loop keeps going. So the term beta is called the feedback factor. And this term AF, which is just V out over VI, that's AF, is what we'd call the closed loop gain. Now, we'll talk about loop gain in a little while, but these are four terms that you're going to need to know and need to remember. Okay, so we're going to come back to these throughout this next few lectures. So based on the block diagram, we can write that V out is equal to the gain, whatever it's going to be A times whatever the signal is at this node right here, right? And that signal is VI minus beta times VO. And so we can see that if we solve for AF, which equals V out over VI, we get, this is A over 1 plus A times beta. This turns out to be an important equation that we'll see again in this lecture. Okay, so moving on to how the gain would get desensitized, one of the primary advantages of feedback, particularly negative feedback. We can, as we just showed on the previous page, V out over VI, or AF, as the book refers to it, is A over 1 plus A times beta. So if we expand this now, and let me just rewrite this a little bit, and I say that V out over VI is equal to, I'm going to factor out a 1 over beta term, and then what I'm left with is a 1 over 1 plus 1 over A times beta. And so what we can see is that V out over VI equal to 1 over beta if A times beta is much, much greater than 1. That is, if this term 1 over A times beta is sufficiently small compared to 1, then V out over VI, or the closed loop gain, is approximately 1 over beta. And this is an interesting result, right? It says that this feedback factor beta will determine the closed loop gain provided A times beta is sufficiently large. So beta is really controlling what our V out over VI is going to be. And all we need is for A times beta to be large, for this to be true. right? Just like we showed with the 741, even though there's quite a bit of variation, A can be large, and as long as beta is a reasonable value, then A times beta is large, and you can use a 741 and have this gain desensitization. So what would an example of this be? In other words, we have variation in A, but our closed loop gain remains relatively constant. Well, we can see that pretty easily if we just look at this inverting amplifier. From the earlier slide, from slide 3, we have this equation for AF, right, or the closed loop gain. And so what I'll do is, let's suppose we design for a gain of 100, that is R2 over R1 is 100, and we're going to assume our resistors are matched, right? And we're also going to assume that we have a sufficiently large A times beta, right? Then we can see that, let's plug in our values for A, R1 and R2 into this equation without making these assumptions and see what the gain turns out. Let's suppose that our amplifier, A here, has a gain of 10 to the 3. If you plug the values of R2 and R1 in, you end up with AF, the closed loop gain, is equal to 90.827. Let's do a few more values. If A equals 10 to the 4th, then AF is equal to 99.000099. This should be negative. And if A is equal to 10 to the 5th, then AF is equal to minus 99.899. And if A is even bigger, 10 to the 7th, we can see AF is equal to minus 99.999. And so you get the idea. As long as A is sufficiently large, our gain, particularly this region in here, is really close to 99, close to 100, right? So this is just an example of how we have these orders of magnitude change in our open loop gain, that is A, but our closed loop gain, AF, remains relatively constant. All right, so let's talk a little bit more about feedback. I'm sure you've all experienced feedback. For example, if you're in a classroom and there's feedback in the microphone, you hear ringing in the speaker, right? If the microphone gets too close to the speaker, you hear this really hideous, loud noise. So what's happening there? So what's happening is you have some sound coming into a microphone here, right? Somebody's talking into a microphone. The signal then comes down into the microphone and gets amplified by an amplifier. The signal then goes up into a speaker somewhere so everyone can hear the person talking, but then some of that feeds back into the microphone and it forms this loop. And now the microphone senses that signal coming in and it amplifies it and back to the speaker, and that signal gets louder and louder and louder, right? And we call that positive feedback. So that would be a case of positive feedback. The signal just keeps growing. So what is the big difference between this type of feedback and the negative feedback that I just talked about on the previous slide? Well, in this type of feedback, the phase of the signal doesn't change. That is, the phase of the signal that we're feeding back is the same as the phase of the signal going out, and therefore it can keep adding onto itself and growing and growing and growing. In negative feedback, the feedback signal that we're feeding back has a phase shift of 180 degrees, so it decreases or it subtracts from our input signal, and it keeps our output signal controlled. So the big difference between these two is that we have a phase shift that we purposely do of 180 degrees when we use negative feedback. Now, the question I would ask is, okay, but how do we know if a negative feedback system is going to be stable? How do we really know? Just because we hook it up, is there a way to evaluate how stable the feedback is going to be? And so to evaluate that, we need to think about what's happening. So this gets a little tricky to understand, but let's walk through it. So op-amps remain stable if the feedback is negative. That is, if we're always feeding back a negative signal, generally we're okay. And what that means by negative feedback is that we have a 180-degree phase shift when we go around the entire loop. So if I'm going to draw what I mean by the entire loop, we start at the output, right? We go back through our feedback beta, which is in this case R2 and R1. We go into the negative terminal through A and back out. That's what I would call our loop, right? So as long as that phase shift in that loop is 180 degrees, then we're going to stay stable in negative feedback. Now, what happens if there's phase shift going on inside the rest of the circuit, or we get some other phase other than 180 degrees? Then is potential to get in trouble. So if we have other phase shift and our total phase shift around this loop here gets to be 360 degrees, or essentially 0 degrees, then the op-amp can be unstable. Basically, what's happening is if we add extra phase shift, we're turning negative feedback into positive feedback. Now, just because we have positive feedback doesn't mean that the situation is unstable. We can have 360 degrees of phase shift as long as the total gain around the loop is less than 1. That is, if we start with a signal here and you go through the loop and come back, but the signal is smaller, in other words, that gain all the way around the loop is smaller than 1, then that signal is eventually going to die out. But if the gain is larger than 1, then the signal is going to get larger and larger and larger, and it's going to grow out of control and become unstable. So if we think about how we would characterize this, what we use is a term called the loop gain. And this is a way for us to quantify the stability of op-amps. And so the loop gain is really a measure of that total gain around the loop that I was talking about on the previous slide. And so we use this value, the loop gain, to determine if an op-amp is stable. And so there's a technique to calculating the loop gain. And to calculate the loop gain, we do the following. First, we set the input to 0. Next, we break the feedback loop. All right? And then we inject a signal called VT or VTest along the feedback path. And then we solve for the voltage, this VR or the V return. And the loop gain is defined as the ratio of VR over VT. That's the loop gain. And in this case, it's fairly easy to see that its loop gain is equal to minus beta times A. Right? This point here is beta VT, and so this is minus beta VT, and so this is minus A times beta VT, and that's equal to VR. You take the ratio and you get minus A times beta. All right, so let's do an example with loop gain. And the example we're going to use in this case is the non-inverting amplifier. So the non-inverting amplifier, the input is going into the positive terminal, right? And we know from other classes that the closed loop gain, AF, is approximately 1 plus R2 over R1, assuming, again, our loop gain is large. So let's, what I'd like to do is evaluate the loop gain for this non-inverting amplifier. And so what we can do is we break the loop, we apply a test voltage, and we measure the return voltage, VR. So in this case, what we would say is that VR is just equal to A times whatever the voltage is on this negative terminal to the op-amp. So we can write that VR is equal to minus A. And what's the voltage at the negative terminal? Well, that's just a resistive divider between R1 and R2. So we can say that it's R1 over R1 plus R2 times VT. Therefore, if we take VR over VT, we can see it's equal to minus A times R1 over R1 plus R2. And we're going to say that's equal to some minus A times beta. And so we can see by inspection, just looking at this term and this term, that beta is equal to R1 over R1 plus R2. And we know from what we learned earlier that our closed loop gain AF is approximately equal to 1 over beta. And therefore, if you put beta, this value into here, you get 1 plus R2 over R1, which is consistent with what we would have gotten had we solved all KCL and derived this value of 1 plus R2 over R1. So in this case, in summary, our loop gain is A times beta, and we can use that sometimes to solve for A and solve for beta. Okay, so we'll continue with feedback in the next lecture, but that is it for today. Thank you.